Let's look at another example of optimal product mix. Activity 3. The Dressbox PLC, a company specialized in men's clothing, manufactures t-shirts in 3 sizes: small, medium, and large. And you are given the details as to the material cost, the direct labor, variable overhead, selling price, and the maximum demand. The fixed cost of production for the period is rupees 1 million. The t-shirts are made from linen material. The purchasing manager advises you that because of the shortage in supply, material supply is limited to 12,000 meters per annum. So therefore, it's a one constraint. So it is the material constraint. Then the human resource manager has informed the maximum labor supply will be 10,000 hours per annum, as the skilled labor takes years to train and are difficult to recruit. Another constraint, that is the labor constraint. The labor would be limited to 10,000 hours. The sales manager has already accepted an order for 300 small, 200 medium, and 400 large t-shirts, which if not supplied would harm the long-term business relationship. So here it talks about the minimum production requirement, and that is also another constraint. The production plan should only be consist of completed unit. So it suggests that it has to be integer values. The product mix should be integer values. Required: determine the optimum production plan to maximize the profit per annum. Fine. So as usual, we may get the required input. So you can copy the information and you can take that to a Excel sheet. So these are your inputs, basically. Inputs. Then here you are given information about the material, direct labor, the variable overhead cost, and the selling price are provided to you. So again, here there are some information that you may have to work out. So probably you need to identify the contribution per unit. So we can do that simply by taking contribution per unit can be calculated simply by taking the sales price and deducting all the variable cost. You have 3 variable cost: material, direct labor, and variable overhead. So there it comes, 350 per unit, that is small size t-shirts. It's 1500 minus 1150 variable cost. So you can simply drag it. So here you have the contribution information. So this is something that you had worked out, an important piece of information. And another information that you might require in the process, that is definitely the product mix. Product mix has to be there. So you need to decide what must be the units to be manufactured. So you can just have a particular number. It's like 100, 200, 300. I might put some assumed figures. And this is going to be your output and one of the important information. And also you would have given the fixed cost information So you can take that fixed cost information as well. The fixed cost was said to be 1 million fixed cost. You can take it 1 million. So you can format this and there it is. In order to maximize the profit, what must be the optimum product mix? So therefore your output is going to be the profit. Profit is what you need to maximize. So how you get that profit? It is simply can apply the sum product and get the total contribution. How you get that? The contribution per unit is there and get them multiplied by the product mix. And that will give you the contribution. In order to figure out the profit, you can deduct the fixed cost. You can take it as a deduction, the fixed cost. So depending on the information what we have fed into the system, so into the model, so there it comes a loss at the moment. So that's perfectly fine because we are going to figure the things out. And now it's time to take the constraint. We have taken some basic information. Now let's take the constraints. In the constraint, the question suggests that there's a constraint as to the materials, the availability was given that the maximum what it can be made available is 12,000 per annum, 12,000 meters, and also the labor availability is given, labor that is 10,000. And also the minimum order requirement is mentioned, minimum order or minimum production, I would say, minimum production as to the 3 products. It is given as respectively 300, 200 and 400. And also it says that the units need to be completed. So it suggests that product mix is an integer. That is also the case. Product mix is integer. You get that. Now when come to the constraint, so there is another useful information that you need to figure out. It is about the consumption or usage. The current usage need to be figured out. So what is the usage? You know, the usage should always be less than or equal to the availability. So I might mention that as well. Availability is the greatest. So in order to get that usage, here you need to know one more information. That's about material per unit and direct labor hours per unit. So let's take that, material per unit, direct labor hours per hours per unit. So how you can figure out the material per unit? It is simply the cost is given per meter, price is given. So all what you have to do, take this and divide it by 400. Then you can simply drag it. So here make sure that you are going to identify the decimal places. So then you can see that material per unit 1.5, material 2.5 and 3. Similarly, the direct labor hours you can work out. The cost is given and per direct labor hour price is given. So you can work out how many direct labor hours it takes per unit. It's 450 divided by 300. So you can simply drag it and again ensure that you identify the decimal places. Now it's fine. You can see that for small, medium and large, the material per unit and direct labor hours per unit are there respectively. Now the usage can be worked out easily. For material, apply some product. You can take the materials per unit and get them multiplied by product mix. Similarly, you can do the same for the labor. The labor you have direct labor hours per unit and get them multiplied by the product mix. Now you have worked the constraints out. Now we can go and apply the solver tool. First we need to set the objective. What is our objective? We need to maximize the profit. Profit need to be maximized. By changing what? By changing the product mix. In doing so, several constraints are there. You need to take that. The first constraint is I might take material. In case of material, the usage must be lower than or equal to the availability. At that, similarly, the labor, the usage must be lower than or equal to the availability. Usage must always be lower than or equal to the availability. The third constraint is that the product mix should always less than or equal to the market demand. So you are given the maximum demand. So the product mix, your product mix should be lower than the maximum demand. Again, the fourth constraint, it's about the minimum requirement. You need to ensure that your product mix is greater than or equal to the minimum requirement. Greater than or equal to the minimum requirement. Minimum order must be accomplished. And finally, the fifth constraint, the product mix should consist of completed unit. It is integer. Now you have added 5 constraints. You can check that. The first one, it's about the material constraint that you had added. It is there. The material, you mentioned that the material usage must be lower than the availability. So that is your fourth one here. And similarly the labor, so that is again the usage must be lower than the availability. That is the fifth. And next we added the product mix should be lower than the maximum demand. So in that your product mix is there and it is lower than the maximum demand, it is the first constraint. And then we mention we need to fulfill this minimum production requirement. Hence, here we have identified the product mix is greater than or equal to the minimum product. And finally, we mention that the product mix should consist of integer values. Everything was perfectly taken. Then we make sure that the unconstrained variables non-negative, that is in the sense. So we want to make sure that what we take to this product mix, there can't be negative numbers. There can't be negative numbers in the product mix, and that's how we ensure that. And what you have to do next, it's about identifying the solving method. As I told you, it's always we assume a linear relationship. So select simplex LP. Now you can solve it. You can keep the solver solution and also the answer. In case of the examination, you need to take the solver solution as well as the answer report. So here we generate that. Now you can see, so this is what our optimum product mix. We can make a profit of 1,550,000 if we produce 500 units of small t-shirts, 1,500 units from medium, and large 2,500. So it is within all the constraints that we had identified. The labor and material fully used, integer values, minimum requirement accomplished, and also it is within the maximum demand constraint. So that is how you work out a question of this nature. In fact, this is one of the past paper questions, and see whether you can manage something of this nature. And I would say this is comparatively easy to the question that we had worked out earlier. So therefore, case of the examination, so we will be testing something that you can manage easily. So with that note, we finish the discussion on the optimum product mix. Now we are going to move on to another application of this solver, Excel solver. We call it using solver for capital budgeting decision. Again, I have just explained on this. So the scenario is something like this. So you are given several projects. So you are in search of the investment opportunity. So therefore you have come up with several investment opportunities. But the problem is you cannot accept all the given or all the viable projects because you do not have enough resources to undertake the project. You do not have adequate financial capital as well as the labor resources. So those would be the two common limiting factors when it comes to the capital budgeting. So when you come across such an instance, so what you should do, so again you can make use of this solver, and it will help you to identify the projects that would maximize the value of the business. The value of the business in the sense, the projects that would maximize the net present value. So again, if you think of doing this in a kind of manual way, so it's a kind of inefficient work in the sense it takes a lot of time commitment and also it takes a lot of effort. So if you make use of this handy tool what is available in your spreadsheet package, so just within few seconds you would be able to come up with the suitable projects. Let's see this through an example. Activity 4. The Vesco Company Limited plans to launch at most 4 software projects in near future. The Vesco company, they want to undertake in maximum 4 software projects, depending on the labor they have, depending on the financial commitments. So they would be willing to accept maximum of 4 software projects. The company has identified 10 potential projects, and following is the information of net present value, cost of year 1 to 3, and labor hours required year 1 to 3 for each project. So you are given information as such. The 10 projects are there, the NPV of each of the project is given, and also the cost that you have to incur in the first 3 years of the project are being given, and together with that, the labor that it takes in the first 3 years of the project, or I would say throughout the project life, is given. So now you are supposed to come up with the optimum projects that would maximize the value of the business. It says that, however, all 10 projects cannot be undertaken due to capital and labor constraint. As always, you can see that several constraints are there. The capital and labor hours available for the year 1, 2, 3 are given below. So here you are given the capital, the money that is available with you in the first 3 years of the project, as well as the labor hours that is available in the first 3 years are given to you. So what are the 4 projects that should be undertaken to maximize the total net present value? Again, so we need to develop the basic model. So we might copy this information. So you can take that information, and that is basically going to be your inputs. The NPV values, cost of year 1, year 2 and year 3, labor year 1, year 2 and year 3 is there. So this is your inputs. Then also we may try to identify the constraints. So the constraints was given here. We have the constraint on the cost constraint, and as well as the labor constraints are there. So now I have identified the capital constraint and the labor constraint. Right. Now what you need to do, so when you are given a kind of application of this solver in this particular nature, so again you need to identify what is your output. So what is your main objective? Your main objective is the maximization of NPV. Maximization of NPV. So here the projects with the NPVs are given. The 10 projects are given with the corresponding NPVs. So how we are supposed to identify the viable projects? So you know that, so if I simply get a column inserted over here, and if I try to identify the acceptance for the rejection of the project, it's like this. I might use ones and zeros to indicate the acceptance and the rejection of the project. Let's say that, so I might just assume that since you can accept like 4 projects, I might take that, assume that project A is accepted. Acceptance is indicated by 1, rejection is indicated by 0, right? Project B is rejected, C is also rejected, D is accepted. I'm just taking some random values, right? So in the sense, I'm randomly assume what are the projects that I'm going to accept. So then the next 2 projects I might not. Project G is accepted, H is not, I is not, and J is accepted. So likewise, I have randomly put some numbers. Even that is even need not to be like 4 numbers, even if you wish. So you can have 5, 6, whatever the number, that doesn't make any difference. But all what it need to ensure that, so you have a kind of way to symbolize the acceptance or the rejection of the project. So here I have chosen ones and zeros. Then if I ask you to get the total NPV of the projects that you would accept, how do you get that? The total NPV of the projects that you would accept. How can you get that particular figure? One sensible way is you can simply look at this particular result and get the value. So 928 is something that I'm going to get. Then plus 543 again I'm taking, and 545 another one, and 841 another. So I'm getting the total NPV, and that is perfectly fine. However, when it comes to the model development, we need to adhere the principles of model development. So it's mostly about effectiveness. So here I feel that if I am to do that in such kind of manner, it will compromise the what you call the efficiency. In this particular scenario, it worked. By looking at these numbers, I have just selected the project NPVs and add that and take the total. But once you run this solver, sometimes these ones and zeros would change. So sometimes project A will become 0, project B will become 1. That is in the sense project A is rejected, project B is accepted, likewise. The different result can come. So therefore in such kind of situation you find that the manual way of doing that, or just taking these NPVs simply by line, it's not going to work. So therefore you need to have a kind of method that is suitable under different circumstances. Hence I would suggest, by using your knowledge on the sum product, you can achieve the same output by doing something like this. See how easy that is. You might take this sum product. Taking the sum product, you can simply ask this first, or the acceptance or rejection column, to multiply by the NPVs. Then you know 1 is multiplied by the particular value, so that is the same value. Once it is multiplied by 0, it is 0. So therefore it will ensure that you are getting the total of the projects that you would accept. එතකොට මෙතන අපි දැක්කා කලින් අවස්ථාවේ මම මොකක්ද කරේ, මේ එක ප්‍රොජෙක්ට් එකෙන් ප්‍රොජෙක්ට් එකට කියන්නේ මේ 1 කියලා තියෙන ප්‍රොජෙක්ට්ස් සිලෙක්ට් කරගෙන ගිහිල්ලා ඒවා එකිනෙකට ඇඩ් කරා. එතකොට ඒ අවස්ථාවේ මේ කියන தත්වය තුළ අපිට නිවැරදි ආන්සර් එකක් වෙනවා. හැබැයි අපේ circumstances වෙනස් වුණොත් අපිට නිවැරදි ආන්සර් එකක් එන්නේ නැහැ. එතකොට අපි සමහර වෙලාවට පළවෙනි ප්‍රොජෙක්ට් එක ඇක්සෙප්ට් කරන්නේ නැහැ දෙවෙනි එක ඇක්සෙප්ට් කරනවා කියලා හිතුවොත් ඒතකොට ඒ වගේ වෙලාවකට අපේ ආන්සර් එක වෙනස් වෙනවා. එහෙමනම් ඒ විදිහට ආන්සර් එක අවස්ථාවෙන් අවස්ථාවට වෙනස් වෙන්නේ නැතුව සෑම වෙලාවකම නිවැරදි ආන්සර් එකක් එන විදිහට මේ total NPV ගන්න අපි හිතුවොත් of the projects accepted අපිට පුළුවන් මේ පළවෙනි කොලම් එක multiply කරන්න කියන්නේ NPV column එකකින්. Now see what happens. So there is something wrong with these values. So let me do the formatting of this. Must be number formatted. And here also get the number formatted. Yes, now it works. Right, 2857. See, now if you change this, still it works. So if you change that and see whether it works, yes, it works. Yes, it works. And here also, I might take the total of the projects that I accept. So therefore, if I simply take the summation, so there would give me how many projects that I have accepted. At the moment, it shows that I'm ready to accept 5 projects. Or since the question says 4 projects, I might simply keep it to 4. It doesn't matter. Even if it is 5, once we run the solver, it will come to 4. But I have just randomly selected 4 projects and it is number 4. Now similarly, if you want to take the cost for the first 3 years, you can do the same thing. In fact, you can simply drag this if you make this first column constant. The first column is for the acceptance and rejection. If you make it constant, you can simply drag that. So then it will give you the cost of the projects that you would accept of year 1 to 3. If you simply drag this, here it gives the cost of the projects that you would accept. So because it's always the total, there it comes where you have 1 in front of that particular cost. So similarly, the labor, you could have taken the same. If you drag this, that's what it happens. So therefore, now you have identified the total cost of the projects that you accept in year 1 to 3, total labor hours that it takes for the projects what you had selected. Since I want to have this total NPV separately, so I might use a different color for this because this is our objective. So these are basically our constraints, right? So here we have this labor, right? Okay. Again, so in order to put this constraint in a kind of more meaningful way, so what you can do is you can take this capital constraint little above, and I might suggest that taking that particular constraint somewhere over here, then it will give you some meaningful context. So it's 2500, 2800 and 2900. So basically that is the availability. So even I can take that, it is the availability of capital. You can take it as the availability. So similarly, if you take this labor in front of this labor, then you can see it is also the labor. Then also in a meaningful way, you can take this as the constraint and even get rid from this. Or since you want to take that labor get appeared, so I might put it to the next cell, next row. So now it is perfect. Now you can even just identify that always the usage has to be lower than or equal the capital, lower than or equal to the availability of capital. So it's lower than or equal. So this does not do anything, but it will help us when we are going to establish the constraint, because this gives us the idea. And also the labor usage should be lower than or equal. It's lower than or equal. It's lower than or equal. Right. Now we have developed this constraint. So when you are given a question of this nature, definitely you have to take this acceptance and rejection, and always you need to go by ones and zeros. Ones and zeros. So therefore this is something which is new to you in the first, since this is the first question, but you need to get used to this. You need to get used to this, right? Okay. Now what we are going to do, we are going to run the solver and figure out what must be the most viable for projects. So therefore this is what we are going to figure out. Okay, so let's go to the solver. Take the solver. Okay, here what you need to do, you want to maximize the NPV. So therefore it's C14. Yes, it's C14. By changing what? By changing this project acceptance A3 to A12. Then what are the constraints? Several constraints are there. First one is, it's about the cost. This cost, the usage of this cost should be lower than or equal to the availability. The availability, it must be lower than or equal. You can add that. Then the labor, similarly, the usage must be lower than or equal to this availability. The usage must always be lower than the availability. The two constraints are added, and also the question had specifically mentioned that the number of projects that you would accept, this particular number should be equal to 4. It must be equal to 4. And that is the third constraint. And the fourth constraint is there. It is not explicit, but you need to know that this acceptance and rejection should always indicate by ones and zeros. So therefore, what you can make sure that having selected this, you can say it need to be binary numbers. You know what are the binary numbers? It's ones and zeros. Ones and zeros. You can mention that as well. Now say OK. See, what are the constraints? You mentioned that the number of projects must be equal to 4, and this acceptance and rejection, it is binary numbers. It can't be anything other than that. It's a matter of ones and zeros. And also you have indicated that the capital usage, the finance, the money that you use must be always less than or equal to your availability. And also the labor usage must be lower than or equal to the availability. And also you need to make sure that this changing variables, the changing variables should not be negative, so you keep it. And most importantly, you assume a simple linear relationship. If everything is fine, you can solve this. You can solve this. You can ask the answer to be kept. See that seems that something went wrong. No, it has worked fine. Earlier the NPV was 3541. Now after the change it's 3628. Earlier we thought of accepting project it's, I would say that it is project B E F J, but now this should be the projects what we should accept. You can see that this is how the projects that you should accept in order to maximize this NPV. In order to maximize NPV, those would be the project that you should accept. And as far as the constraints are concerned, almost all the constraints are non-binding. You have enough resources, but the only constraint is that binding one is you have mentioned you can accept in maximum for project. So if you look at the money, yes, so you can see, so that is money is adequately available, and also the labor, that is adequately available. So but the only constraint is that you can accept in maximum of 4 projects. So therefore you have confined to 4 projects. So that's how we work out the capital budgeting using your knowledge on Solver. So in order to convince ourselves, we may work out one more question. It's a kind of exam question. So I have selected, that is your activity 5. See, the marketing and research division of the company has analyzed the net present values of different market segments. Details are as follows. You have identified several market segments: women t-shirts, men's shirt, women's skirt, likewise. The maximum investment that the company can afford is 6 million, and the maximum labor hours available will be 25,000 hours. So that is basically the constraint, and the investment cannot be divided. Investment cannot be divided. So if this is the situation, you need to determine what are the investment that the company should undertake in order to maximize the net present value. Again, as usual, you can copy this information. You can copy the information and take it to a kind of new sheet. So this would be the information that is given. Again, so you are given the constraint. The constraint is that two constraints are there. The maximum investment that you can go for, the constraints that you can go for, the capital investment that the company can afford is going to be like 6 million. In maximum company can afford 6 million, and labor hours, that is 25,000. Then again here the acceptance and rejection must be identified, because I told you that it is in the same structure. You need to get that. Some of these projects would be accepted. It's acceptance, accept or reject. So you can take it. So I might randomly pick 1, 0, 1, 0. Likewise, I might put them in a particular order, right? So I'm just taking some random numbers. So here they haven't mentioned that how many projects that they can undertake, but what it says, the investment cannot be divided. So if you are going for a particular investment, you need to undertake that full, otherwise you need to give it up in full. Let's take the total NPV. So in fact you can first identify the investment by applying this sum product. So you can work out the cost of, or the initial investment that it requires for the projects that you accept. You can make it constraint and you can get the investment. 6,500 at the moment. So if you simply drag this, this is it. So what you want to do, you want to maximize the NPV by changing this, by changing the projects that you would accept. So the constraints are there. It is just to mention, investment must be less than or equal to 6,000, and also the labor must be less than or equal. Let's go and work out the solver. It is going to be set objective. It is the NPV that you want to maximize by changing what? By changing the projects that you may accept or reject. The constraints are there. The first constraint is that the investment must be less than, the usage must be less than or equal to this constraint, and the labor hours usage must be less than or equal to the availability, and also this changing cells must be binary, either accept or reject, accept or reject, accept or reject. Yes, it seems that those would be the three constraints that is there: investment, labor, and the binary. Make unconstrained variables non-negative. You want to make sure that the changing variables are not getting negatives. The relationship is simple linear relationship, and solve it. Take that together with the answer, say OK. So this is the situation. So you can accept three projects. So where you can see the investment is getting 6 million. So the amount that you use is exactly equal to the amount that is in hand, and the maximum NPV that you can go for 1.55 million. And yes, so it is the three projects that you accept. So this is how we work out the capital budgeting decisions using solver.